Welcome to Theory of Computation. This is lecture number 20. In the last lecture, we were discussing descriptive complexity. As I told you, descriptive complexity is also called Kolmogorov or Kolmogorov-Chaitin complexity. Essentially, if you have a string x, the descriptive complexity of x is the length of the smallest description of x. But we have a very precise notion of what a description is. The way we describe strings now is by first describing a Turing machine and then concatenating that with another string. So a description is a description of a Turing machine M followed by another string W. The way we obtain the original string back is we run this Turing machine on the string W. So you can think of it this way. In order to describe a string, you first give an algorithm and some data for that algorithm. So the person who receives the description can run the algorithm on that data, and that would produce the string x back. The length of the shortest description is called the descriptive complexity of x. So this is an extremely general way of compressing strings. What we are saying is that the description length of a string is the length of the smallest algorithm, the shortest algorithm that produces that string. I gave you as an analogy the programming language Java. When you download a program and run the program, it produces some data for you. What was intended to be communicated to you was that data, but that data was not sent across. Only the program was sent across. We proved some basic theorems about descriptive complexity. Now, today's lecture is going to be a continuation of that lecture, and the outline of today's lecture is as follows. We would once again start talking about incompressible strings. After that, we will further discuss some theorems on descriptive complexity. Then today we will move on to a new topic, which is going to be complexity theory. After that, we will review some notation that is going to be needed when we study complexity theory, namely, we will review the big O and the small o notation. So let us begin. What was an incompressible string? An incompressible string was a string whose description was at least as long as the string itself. So these are strings that cannot be described by fewer bits. All the bits are in some sense essential. The description of the string is at least as long as the string itself. What we did was we proved a few theorems about it. Let's begin. Let's recall that a string x is called B-compressible if its descriptive complexity is less than or equal to the length of the string minus b. So, in order to describe this string x, what we can do is save at least b bits. So a string is B-compressible if its description is at least b bits shorter than the string itself. A string is B-incompressible if it is not B-compressible. And a string is called incompressible if it is not one-compressible. Incompressible strings cannot be compressed. Their description is at least as long as the string itself. So that's the notion of incompressible strings. We also proved a few theorems about incompressible strings. In fact, we proved that there are incompressible strings of every length. Furthermore, we said that if you fix a b, then we can at least have these many strings of which are incompressible and have length n, which are b incompressible and have length n. The other thing we said was that incompressible strings look like random strings. This can be made precise in many ways. So, we are talking about incompressible strings, and what we want to say is these strings look random. That's quite intuitive, because if a string is incompressible, then it cannot have any patterns in it. Because if we find a repeating pattern in a string, then we can use that pattern to describe that string in a succinct way. Thus, incompressible strings have to look like random strings. We prove the following two theorems. For every n, there is an incompressible string of length n. The second theorem was that the number of b incompressible strings of length b is at least 2 to the n minus 2 to the n minus b plus 1 plus 1. The proofs of these theorems is simple counting. The way we prove these theorems is by simply counting. One thing that is very clear about descriptive complexity and description of strings is that if you take two strings x and y which are distinct, then they must have a different description. This is easy to see because from the description we have to be able to compute x and y. Now, if x and y will have the same description, it would not be possible for us to decode x and y back. Thus, any two strings must have different descriptions. The other thing that we observed was that the number of descriptions of length less than or equal to n minus 1 was 2 to the n minus 1. That's just a simple geometric series and you can add it up. On the other hand, there are 2 to the n strings of length n. Therefore, at least one of them must be incompressible. The other theorem was also simple counting. We counted the number of descriptions of length n minus b, with a number of descriptions which have length less than or equal to n minus b. And 2 to the n is the number of strings that have length n. So 2 to the n minus that quantity must be the number of strings which are b incompressible. These were two very simple theorems, but what they do is they show that incompressible strings must exist. In fact, this is going to be a theorem no matter what compression scheme you come up with. You will always have one string which is not compressible. Then you can ask, if that is the case, why do compression schemes work? Well, there's a very good reason for compression schemes to work in practice. In reality, what happens is not all strings are equally likely. So, for example, if you take English text, it cannot be just random letters permuted. It's made out of words and there's a pattern in it. E is usually the most frequently occurring letter. So, what compression schemes do is the files that are more likely to arise in practice, it maps them to small descriptions. And on the other hand, mumbo jumbo, which is never going to ever come up in, say, human conversations or human writings, that is mapped to things which have larger descriptions. Thus, in practice, we get compression. Well, we're studying this thing from a very theoretical point of view. So, let's now begin. I told you that incompressible strings look like random strings. So, if you take a random 0-1 string of length n, it's going to contain roughly 50% zeros and 50% ones. So, an incompressible string must also have that property. Another property of random strings is that if you take a random string of length n, the longest run of zeros that you would find in it is going to be of order log n. That's a reasonably simple fact to prove about random strings. Well, incompressible strings must have this property. So if you have an incompressible string, the longest run of zeros that it can have is going to be order log n. But incompressible strings are extremely random looking. What we will prove is an extremely general theorem which would say that every incompressible string must look like a random string. In some sense, what we are saying is, suppose you make a test for randomness. So, if you take a random sequence, it will pass that test. On the other hand, if a sequence is not random looking, it will fail that test. Well, any computable test that you can make for checking randomness, incompressible strings are going to pass that test. For this is an extremely general statement, and for this, we'll need to define the notion of properties of strings and when a property is true for almost all strings. Let's begin. A property that holds for almost all strings also holds for incompressible strings. This is the general statement we will prove. But we have to formalize this statement. A property P is just going to be a mapping from the set of all strings to true false. Thus, P is just a mapping from 0 1 star to true false. This mapping actually classifies the strings into two classes. The first class which has the property and the second class which does not have the property. So every property is just taking strings of zeros and ones and just assigning it true or false, which means it says these are the strings that have the property and these are the strings that do not have the property. For example, P could be that a string has exactly n over 2 zeros. Well, this is a property, but it does not hold for almost all strings. Well, let's see what we do with this. We will say that P holds for almost all strings if we consider the set of strings of length n for which the property is false and divide it by 2 to the n, then this ratio approaches to 0 as n approaches to infinity. So a property holds for almost all strings if you look at the number of the fraction of strings of length n which do not have this property. If that fraction approaches 0, so what it means is as n becomes larger and larger, fewer and fewer in terms of percentage strings have this property, and that ratio approaches 0, we say that this property holds for almost all strings. The theorem we will prove is if P holds for almost all strings, and if you take a number B which is greater than 0, then this property is false on only finitely many strings that are incompressible by B. So any property that holds for almost all strings can be false on only finitely many incompressible strings, finitely many B and incompressible strings. This means for the rest of the incompressible strings, this property must be true. So all the remaining strings which are B incompressible would look random to this property. Of course, if a property holds for almost all strings, then it also holds for a random string with high probability. Well, let's start proving this theorem. We start by looking at the following algorithm that is given to you on your screen. This algorithm takes as input an integer which is given in binary. Now what it does is it goes lexicographically through all strings and finds out if f of s is true or false, or if the string has the property or not. Every time this string does not have the property, it increments a counter. And when the counter reaches I, it just outputs that string s. So this is a very, very simple algorithm. It takes an index I and it goes through all possible strings lexicographically and it finds the ith string for which this property fails. So if you give this algorithm 50 as input, it will find you the 50th string for which this property fails. So this is a very simple algorithm. The main point is this algorithm can be used to describe strings for which this property is false. Let's have a look at this. We can use M to obtain short descriptions of strings that do not have the property P. Let X be a string that does not have a property P. Let I sub X be the index of X in the list of all strings that do not have the property P ordered lexicographically. Then now, suppose what I do is I take this algorithm which I call M and append I sub X next to it. Well, this is a description of a string. How do you decode this string? You apply this algorithm on I sub X. So this algorithm will go and output the I sub X string which does not have the property P. But by definition, that string is X. So M followed by I sub x is a description of x. Let us look at what is the length of this description. The length of this description is the length of I sub x plus a constant c. The constant c is added here because M has some fixed length, which is a constant, followed by I sub x. So it's going to be the length of M properly encoded. So actually we repeat it twice. So it's 2m plus 2 plus I sub x, and we have collected all those terms into a constant. This description simply says the ith string not having property p. So in English, if you were to describe this description, it says, well, I'm talking about the I sub x string not having property p, and by definition that string is x. So we have a description of string x for which this property is false. Now let's count. Suppose you're given a b greater than 0. We will select n such that at most 1 over 2 to the b plus c fractions of strings of length less than or equal to n do not have the property. Why can we do this? Well, remember that p holds for almost all strings, and therefore the strings of length n on which p is false, the fraction of that approaches 0. So we can take n large enough which satisfies this property. Note that since p holds for almost all strings, we can always find such an n. This is true for sufficiently large n. Then we can have I sub x is going to be less than or equal to 2 to the n over 2 to the b plus c. Since there are only 2 to the n over 2 to the b plus c strings which are for which the property fails, therefore if we count the total number of strings up to length n, that's going to be less than or equal to this fraction. So now it is clear that I sub x is going to be less than or equal to that same quantity. Therefore, the length of I sub x is going to be the log of this quantity. Now the length of I sub x, if you calculate, it turns out to be less than or equal to n minus b minus c. Hence, the length of m followed by I sub x is at most n minus b minus c plus c, which is equal to n minus b. Therefore, the descriptive complexity of x is less than or equal to n minus b. Well, if the descriptive complexity of a string is less than or equal to n minus b, which means you have saved b bits by describing it in a clever way, then that string is called decompressible. So this means x cannot be decompressible. This shows that if x is decompressible, then p of x equals true, then the length of x must be less than n. So this shows that if x is incompressible, then either p of x is true, x has the property, or the length of x is less than a fixed quantity n. But now the number of strings whose length is less than a fixed quantity n is only finitely many. Therefore, the property p can fail on only finitely many incompressible strings. So what have we shown? We have shown that if a property is true for almost all strings, then it must be true for all but finitely many decompressible strings. What this says is that, remember that if a property holds for almost all strings, then it would hold for a random string. Thus, it says that incompressible strings will look like random strings. You can think of this property p as a test for randomness. Any number that passes this test, you say it is random looking. And what this theorem is saying is, other than finitely many incompressible strings, all the other incompressible strings will pass this test. And this test can be any computable test. Now, let us ask a very interesting question. One very interesting question comes to our mind is, can we compress compressed data? If we could do that, that would be very useful and very interesting, but obviously you would realize that it would also be very paradoxical, since what we could do is we could take data, compress it and reduce it, and compress it again and reduce it and compress it again, and this would tend to tell us that eventually we'll get rid of all the data, which seems absurd. So intuitively it seems that the answer to this question of whether compressed data can be recompressed again is no. And of course, intuitively that's the answer. Let's try to prove this formally. What we will prove is there is a constant b such that for any string x, the minimum length description d of x is incompressible by b. So roughly what we are saying is, if you take a string and you take its minimum length description d of x, you cannot further compress its description. How would we go about proving this thing? Rough idea is, suppose we could compress this description by a lot. Well, then what we can do is we can take the string x, compress it to get the description of x, which is minimal length, and then recompress that, and we'll get a much shorter description. Now, this new description is also a description of x. So all we have to do is communicate to our friend that whatever data is being sent, you have to decode it twice. And this way, we would have actually compressed x by more than what it was compressed before, which would be a contradiction. Let's prove this theorem formally. We start with the following Turing machine M. What it does is, on input r and y, it first runs r on y and looks at the input, which is going to be of the form s comma z. Then it runs s on z, and whatever is produced, it just writes that on its output tape and halts. So this Turing machine essentially is decoding twice. It gets a description and a string, and it runs that Turing machine on that string, which outputs another Turing machine and a string, and it reruns that Turing machine on that string. So what this Turing machine is doing is decoding twice. This Turing machine, or this algorithm, is a fixed algorithm, and therefore it has a fixed size description. And what we can do is use this description, which is essentially saying decode twice, in order to get another description of x. Let us take the constant b to be twice the length of this description plus c. We now show that b would satisfy the statement of this theorem. Suppose, on the contrary, that d of x is b compressible for some string x. So let's take a string x whose description can be compressed more than b. Well, what we can now do is use this Turing machine M to describe x in a shorter way. Let's see. Suppose that the description of x is less than the description of x minus p. But what would happen if we run this Turing machine M on d of x? It would output x. So this Turing machine, when I run it on d of x, since it decodes twice, therefore it would get back x. Thus, M followed by d of x would be a description of x. Well, let's ask, how long is this description? So what we want to do is estimate the size of this description. The first part of this description is just b bits. What about the rest? Well, that has size d of x, the size of d of x. The first part is equal to b minus 1, and the second part is equal to the length of d of x minus b. Remember, because we said that d of x was b compressible. If we add this all up, we get that the length of this description is d of x, the length of d of x minus 1. But this is a description of x, and it's smaller, one bit smaller than d of x. That contradicts the fact that d of x was the shortest description of x. This concludes our discussion of descriptive complexity. This is the last theorem that we are going to prove about descriptive complexity. There are very interesting theorems in this area, but we are not going to go further in it. This also concludes the first part of our course, which was computability theory. Let's just simply revise what we have learned in computability theory. The first and the most important accomplishment of computability theory is the definition of an algorithm, a formal definition, mathematical definition of an algorithm, which is that an algorithm is equivalent to a Turing machine. Then there are some very major theorems there. There is this whole theory of the halting problem. We showed that the halting problem is not computable, in the sense it's not decidable. There cannot be an algorithm that can decide the halting problem. After that, we looked at several problems from different areas of computer science and said that many of these problems are not decidable. We looked at Turing recognizability. We also identify sets which are not Turing recognizable. We even identified sets which are not Turing recognizable and not co-Turing recognizable. Then we studied other problems in logic. We started looking at decidability of logical theories, and we proved some very interesting theorems there. What we did was we proved that number theory is not a decidable theory. On the other hand, we showed that Pressburger's arithmetic is decidable. Then we also studied the recursion theorem. The recursion theorem was a very beautiful theorem which said that a program can somehow obtain its own description and perform self-analysis. We use this theorem to prove several things are undecidable. We also use this theorem to actually construct a sentence in number theory which was true but not provable. That is actually Gödel's theorem. We actually saw a proof of this great theorem, Gödel's theorem, that says that in number theory you can write sentences which are true but not provable. After that, we looked at descriptive complexity. Descriptive complexity is actually talking about what, or trying to formalize what information is, how much information is present there in a given string. We looked at several theorems in descriptive complexity. They were very interesting. One thing that I would like to mention is this function k of x, which is the length of shortest description of x, is not a computable function. This is one of your exercises. Furthermore, it is also true that given x, computing d of x is not possible, which seems to say that this whole theory that we have built is useless. But this is not the case. Very deep ideas have come out of descriptive or Kolmogorov complexity. So this was part 1 of the course, which was computability theory. If we think a little hard about computability theory, we were trying to classify problems which were either decidable or not, problems for which algorithms exist and problems which cannot be solved by algorithms. However, if we think about it more, we realize that if there is a problem for which an algorithm exists, but that algorithm is so inefficient that when you run it, the computer just keeps running forever and it gives an answer. It's supposed to give an answer, but the answer will come years from now. Then, of course, that algorithm is not very useful. So somehow, we were not studying algorithmic questions very delicately. What we assumed was we had unlimited memory and unlimited time. And the question was whether a problem can be solved using unlimited memory and unlimited time. the next part of this course is going to be complexity theory. Here, the theme is not whether a problem is decidable or not, but how complex or how complicated it is to solve. So, what we will do is, we will look at now problems more closely. So, complexity theory only looks at decidable questions. So, we will now look at languages which it's going to be absolutely clear are decidable, that we can devise algorithms which decide these languages. So, we would look at problems for which we have algorithms. These problems are solvable by algorithms. Then we will ask the question whether we can have an efficient algorithm or not. That is a more practical question and a more useful question. What we will do is, we will now measure space and time and other resources used by an algorithm. So, a typical question in complexity theory would state a problem, a language, and then say, what is the most efficient algorithm that we can have for this problem? Or it says, can we identify how complex this problem is in terms of the time required to solve this problem or the space requirement of this problem? This is going to be the next part of this course. In order to study complexity theory, we will have to review some of the definitions that you already know. So, let's begin. Now we will look at resource-bounded computations. Two of the most important resources that we are going to study are time and space. Let us take an example. Let's take a concrete example and see what we mean by time and what we mean by space. So we will start with a language. We will look at an algorithm that is going to decide this language, which is actually a Turing machine. And now we will say, how long does this Turing machine take to make its decision? So, as an example, let us consider the language A, which is 0 to the k, 1 to the k. So, the language A consists of strings which are a certain number of zeros followed by same number of ones. What we want to do is decide this language. So, all we have to do is present an algorithm. As you know, there's a very simple algorithm which we can use to decide this language. That algorithm is now given to you on your screen. This is a Turing machine that accepts A. What it does is, it first scans the input, and if it sees any 0 before a 1, it makes sure that all the zeros appear before a 1. If not, it will simply reject. Then it will scan across the tape, crossing a 0 and a 1 each time. And if zeros are remained and ones finish, then it rejects. If ones remain and zeros finish, it rejects. And if both zeros and ones are finished, it accepts. Otherwise, it repeats the same process. So, this Turing machine scans the tape, crossing off a 0 and a 1 every time. And it scans the tape again, crossing off a 0 and a 1 the next time. So, what we will now do is ask, how many steps does this Turing machine take? What is the time required by this Turing machine? Well, let's try to have a rough estimate. Suppose the length of the string that you had was n. So that means you had about n over 2 zeros and n over 2 ones. This machine is roughly going to make about n over 2 passes over its input in order to cross off all the zeros and ones. So, roughly the number of steps taken by this algorithm would be order n squared. Now, the question arises whether this is the best possible algorithm or not. Can we come up with another algorithm which actually decides this language, solves the same problem, but does it in fewer steps? That is the central question in complexity theory. So, let us review some definitions. A step of the Turing machine is assumed to take a unit time. Let's start with the definition. Let M be a Turing machine that halts on all inputs. So, M is a decider. The running time or the time complexity of M is a function from natural numbers to natural numbers such that f of n is the maximum number of steps that m uses on any input of length n. In this case, we will say that m runs in time f of n, or m is a fn time Turing machine. So, see, the running time of a Turing machine cannot be a simple number. It has to be a function of the input. But what we do is we collect all inputs of same size and take the maximum. So in some sense, we're saying, well, what is the worst case performance of this algorithm or Turing machine on inputs of length n? And we assign that number f of n. So running time of a Turing machine is a function f of n. And we assume that this Turing machine is a decider. What kind of function we would get if we take a typical Turing machine and try to calculate its running time? Typically, this function is going to be extremely difficult to calculate. Not only that, it's going to be very strange. But what is good and what we will do is we will realize that most of the time we cannot exactly calculate this running time, but we can estimate it in a meaningful way. In order for us to talk about what estimates are, we have to build a formal notation that you have studied before in your algorithms course that is called the big O notation. So let us review this notation. What we want to do is understand how much time a Turing machine takes in the worst case. The exact running time, T of n, is going to be a very complicated expression. In some cases, we'll not be able to compute it precisely. But what we are interested in is getting the rough idea about how Tn grows for large inputs. So we will use asymptotic notation. Asymptotic notation is going to help us understand the growth pattern of this function. So we're not going to understand this function in complete detail, but how it grows. Let's look at example. Suppose that we have a function f of n that happens to be 5n cubed plus 13n squared minus 6n plus 48. This function has 4 terms. As you know from your pre-calculus and calculus classes, n cubed grows much faster than n squared and much faster than n. So if n is large, the bulk of this, the amount of this function or the total sum in this function comes from the term 5n cubed. So 5n cubed in some sense summarizes this function. What we're doing is ignoring lower order terms. Well, in the big O notation, what we will do is we will also ignore constants. So we'll throw away 5 and we'll say this function is order n cubed. What we are saying is that the growth pattern of this function is something like n cubed. But we want to make this notion mathematically precise. If we study 5n cubed, we realize that the constant 5 does not contribute to the growth of 5n cubed. Thus, if we ignore 5, we can say that f of n is order n cubed. We will denote this by f of n equals big O of n cubed. Let's state the definition of the big O notation precisely. Suppose you have two functions g and n which map natural numbers to the positive reals. We will say that f of n is order g of n if we can find two positive constants c and n naught such that for all integers n greater than n naught, f of n is bounded by c times g of n. When we say f of n is big O of g of n, we will say g of n is an asymptotic upper bound on f. Sometimes we will just say that g of n is an upper bound on f. So, when we say f is big O of g of n, what we mean is there is a constant c and n naught. The n naught says you are allowed to ignore the first finitely many values of f and g. But after that point, this function f must be bounded by c times the function G. So in some sense, the big O notation says that f cannot grow much faster than G, or more precisely, f cannot grow faster than a constant times G. So when I say that f is order n to the 7, what that means is f does not grow faster than a fixed constant times n to the 7. Here, there is a very important question that you may ask. You may ask that when we are using big O notation, we are ignoring constants. Why are we doing that? Well, there is a very simple reason for it. Imagine that you have a program, and I tell you that this program runs in time n squared. If you run it on a particular computer and you give it an input of length n, then it runs in order n squared on my computer. But suppose you take that program and run it on your computer, and you seem to have a more modern version of the computer. You just bought a brand new laptop, so it's a 2 gigahertz machine, whereas my machine was an old P2 which was running on a few hundred megahertz. Well, it will appear to you that the program runs faster on your computer. What is happening here is your computer is faster, and therefore it takes every step much faster. So what happens is different computers will run the same program at different speeds. Thus, they will have a different constant attached to this time, which I've said is n squared. So the computer may run in n squared seconds on my machine, but it may run in n squared over 50 seconds on your machine, because your machine is 50 times faster. This means that constants will be introduced according to which machine you run this program in. Thus, these constants are not inherent properties of algorithms, but they are actually coming from hardware implementation or the implementation of the software that you have. We are not interested in those things. We are interested in intrinsic properties of algorithms. The order at which the time complexity grows is an intrinsic property of that algorithm. That algorithm, if it's run on a slower machine, will run slower, and if it runs on a faster machine, will run faster. And therefore, we ignore these constants, and the big O notation is designed to do this. Therefore, what it does is it captures an intrinsic property of the algorithm. Let's continue. Intuitively, what we will think is f of n is big O of g of n. You can think that f is less than or equal to some multiple of g. For most functions, the highest order term is an obvious candidate to be g. Let's look at this example. In this case, f of n is 13 times n to the 4 plus 7n squared plus 13. So, f of n is big O of n to the 4. Furthermore, we can also say that f of n is big O of n to the 5. But it is not true that f of n is big O of n cubed. You may ask, why is it that f of n is order n to the 4 and it is also order n to the 5? Remember, the big O notation says that the function which goes inside the O is an asymptotic upper bound. It does not say that it is the best possible asymptotic upper bound. In your algorithms courses, you must have heard of the theta notation. Theta notation says that this is the best possible upper bound. We will not use theta notation. We will just use the big O notation. I just wanted to clarify that if you have any upper bound, then if you take a function which grows faster than that upper bound, then you can say that the faster growing function is also an upper bound. Don't let this confuse you. For example, I could make a very simple statement which says pi, the famous pi, which is the ratio of the circumference of a circle with its diameter, for example, I can say pi is less than or equal to 4. Well, so I'm giving you an upper bound for pi. Pi is also less than or equal to 5. That's also a true statement. Pi is also less than or equal to 500. That's also a true statement. So the big O notation only establishes an upper bound. It has nothing to say about whether that upper bound is the best possible one or not. What we're saying is that we have an asymptotic upper bound in the big O notation. Let's look at a few more slightly complicated examples. Suppose that f of n is log to the base b of n, where b is any number. You can think of base 10 or 20, but b is a constant. Now, we know that log to the base b of n is equal to log to the base 2 of n over log to the base 2 of b. Hence, we can say that f of n is order log of n. Why is that? Because log to the base 2 of b is a fixed constant. So, log to the base b of n is order log to the base 2 of n. Let's look at another example. Suppose that we say that f2 of n is 5n log n plus 200n log n plus 17. Then we can say that f2 of n is equal to order n log n. Why is that? Because n log n grows faster than n log n. Log n grows faster than log n. Let's continue with our examples. We can also use the big O notation in exponents. However, we have to be careful. Suppose I write 2 to the order n. This stands for a function that is upper bounded by 2 to the cn for some constant c. In this case, when the constant appears in the exponent, we cannot ignore it. So, if somebody says, I have a function which grows like 2 to the order n, that means they're saying that they have a function which is upper bounded by, asymptotically upper bounded by 2 to the some constant n. Remember that now it's not the case that 2 to the n is order 2 to the 2n. That's not true. Therefore, in this case, the constant becomes important. Let's look at another example. Let's say somebody says that they have a function which is, they talk about the function 2 to the order log n. Well, remember that order log n in some sense has a constant attached to it. Thus, this time, this means that they have a function which is upper bounded by 2 to the c log n. Now, if you compute 2 to the c log n is equal to 2 to the log n all to the power c, which is equal to n to the c. So they're saying that they have a function which is of the form n to the c. So c here could be any constant. So this means that they're saying their function is bounded by either n squared or n cubed or n to the 5, but they have not told you the exponent. So they are just saying that they have a function which is bounded by some polynomial. However, they've not told you the exponent of that polynomial. Bounds of the form n to the c will be called polynomial bounds, whereas bounds of the form 2 to the n to the c will be called exponential bounds. Polynomial bounds are what we will be very interested in. Suppose we have an algorithm that runs in polynomial time. We would say that that algorithm is practical. This is going to be the rough definition of what a practical algorithm is for a theorist. Although theorists are not really very interested in practical problems, but nevertheless, this is the definition we'll take of an algorithm that is a good algorithm. This definition was initially given by Jack Edmonds, who described a good algorithm for finding the largest matching in a graph. And he showed that he could find the largest matching in a graph in polynomial time And in that paper, he argued that this was a good algorithm because it took polynomial time, and this was a definition of what a good algorithm should be. On the other hand, Jack Edmonds also conjectured that the traveling salesman problem, which we will discuss later and which you must have heard about, does not have a good algorithm. This conjecture of Jack Edmonds, I think, has become the most important problem in computer science. In the next lecture, we will start looking at Turing machines, time complexity, space complexity in a formal way. We will define what complexity classes are, and we would ask extremely important and central questions in computer science. I'll see you next time. Thank you and goodbye.